Hey everyone, this is Ayush, and today I'm going to explain you binary search from like all basics to everything you need to know about this binary search. After this video, you will be able to learn how to implement binary search and when to apply it, and you'll master the binary search. I can guarantee it. So, without further delay, I'll just get into it. So, what we'll discuss in this video is what is binary search and how is it different from linear search, right? And when can we apply this binary search, how and why to apply binary search. This is very important. The structure of the video, it is very organized, and we'll discuss one example, few examples. I will write pseudocode for it as well in this ipad itself, and we will write actual code itself, so you will understand pseudocode. You will be able to write this code in any language, so that won't be a problem. I'll be doing it in C++, and we will discuss how to prevent overflows. This is very important concept for interviews. uh, at last, we'll discuss time complexity and space complexity of this approach. So without further delay, let's get into the first topic, what is binary search and what is linear search. What are these concepts roaming around, and why is it so popular? Why is it so important topic for interviews, for software interviews? So we'll take an example, like uh, just take a simple example. We find the index of target element, right? This is our target and this is our array, right? We have target as 23 and we have to find this element in our array. So how do we do it? Ekdam traditionally, ekdam in simple way. How do we do it? So what we do is check each element, move element by element, and check if the element is equal to target, right? And if we find that element equal to target, then I have my answer as that index, and I'll return my answer, right? So we'll discuss linear search first. What do you do in normal approach, ekdam simple approach? What do you do in linear search? You will traverse your array from first element, which is 0th element here. You will check, is this 2 equal to let's do it like this. Yeah, so is this 2 equal to my target? Is 2 equal to target? No. Then you will move forward. This is your pointer now. Now you will check, is 5 equal to 23? No. So you'll move forward again, and now you will check, is 8 equal to 23? Is 8 equal to, no? Then we'll move forward to 12. Is it equal to 23? No. Then we'll move to 16. Then we'll move to 23 similarly, right? So now we find 23 is equal to target, which is 23, right? So what we'll do is return this index 5, and this is our answer, right? This is linear approach, total simple approach in which we can traverse the elements one by one and see if that equal to our target. And if I find that element to be equal to my target, then I'll just return that index. As simple as it, right? Now this is the linear search. I'll go element by element. I'll go element by element, one by one, one by one, one by one, till I find my element. If I reach the end of the array, let's say this was array of size 10, right? And if I reach my I equal to 10, and initially my I was equal to 0, I equal to 1, and go so and so forth. If my I becomes 10, that is, we reach end of the array, we go out of bounds, then I can say my element does not exist, right? This is the normal approach in which we do our thing. This is linear search. So what is binary search now? In linear search, what we do is traverse each element one by one and try to check that if this element is equal to target or not. But in binary search, what we do is, now this is our whole search space, right? From here, this index to this index, this is our search space. And what we do in binary search is pick a midpoint. Midpoint of this is this is denoting this by low. This is low pointer, and this is high pointer. Low pointer denotes the start of our search space, and high pointer denotes end of our search space. And let's say we have to find middle of this, right? So low plus we'll find middle of this by adding both and dividing it by 2, taking average of them, right? So it is 0 by plus 9 by 2, which is floor division would give, integer division would give you 4. So this is our mid. Now what binary search does is helps me eliminate one half. How do we do it? We'll look into it. But so what is binary search? We have our search space. We divide our search space into two halves, and we eliminate one half of the search space. So this reduces our effort to search into other half, right? If you divide the array into two halves, you will be able to eliminate. If you are able to eliminate one half, then obviously your this work has been saved, right? You don't have to search this remaining half now, right? So this is that's how it's different from linear search. I'll discuss how we are going to implement this and how exactly things work. So let's discuss the second point now. Like, when do we need binary search? Binary search is only applicable when our search space, like search space in the sense, like in this case we are talking about this array, right? This is our search space. We will search our target in this search space itself. So when to apply binary search, we will apply binary search only if and only if our search space is monotonic. What is monotonic? Our search space should be like increasing or decreasing, to be specific, non-increasing or non-decreasing. It should be sorted, to be honest. Yeah, so if my search space is sorted in any order, let it be non-decreasing order or non-increasing order, like 1 2 3 4 or 5 4 3 2 1, anything, it should be in sorted order, then I can apply binary search. So how to apply binary search, we will learn this by example, and why to apply binary search, we will discuss this in time complexity as well. But yeah, to simplify, we will get into how do we apply binary search soon, like in this example itself. Why to apply binary search? It is as simple as, like in linear search you have to go through each element one by one, and this would in worst case we would have to check each element, right? So we would have to traverse entire array, right? But in binary search we don't have to traverse entire array if the array is sorted. So if array is sorted, we don't have to traverse. Like, this is how we will come to that. How are we saving our time? How are we like eliminating our search space? Let's get into it. So for like implementing binary search, we need two things. We need like 3 pointers. Like, first is low pointer. Let's erase it. Low pointer. We will assign low pointer to start of our search space, like here, and we would assign high pointer to end of our search space. I know that if target exists, like we have target is 23, right? If it exists, it would lie between this search space itself. Got it? Okay. Now I'll explain the algorithm and you follow through it, and we will discuss pseudocode, so it will be more clear later. So what happens is, like, as I said, we have the search space. Now I'll find a midpointer for the search space, which is exactly in between of low and high. So to find mid, what I can just do is mid equals to basically low plus high by 2. This is integer division. So in this case, my mid would be equal to, what would be my mid? It would be like current low is 0 and current high is 9. So 0 plus 9 by 2, which is 4.5. So integer division would give me just 4, right? So my mid pointer is here, points to index, like 4th index of the array, which is 16. So now what I'll do is check, is this 16, is this array of mid, is this 16 equal to my target? Is this 16 equal to 23? No. So my 16 is not equal to 23. So this is not my answer. Now about eliminating the search space, I know that 16 is lesser than 23, right? 16 is lesser than 23, and 16 is basically array of middle element which is less than our target, right? So the element which the mid pointer is pointing to 16, which is now currently lesser than my target. So I know for sure, like, this is lesser than target. This is monotonic sequence, right? We have increasing monotonic sequence. Makes sense? So I know that my 16 is like lesser than target. So I know any number which is like smaller than 16 won't be my answer. 16 is smaller than target, so 12 is also smaller than target, 8 is also smaller than target, 5 is also smaller than target, and 2 is also smaller than target, right? So that's why I can say that anything here in this half, like our array is now divided into like this half and this half, right? So I can say that my target does not lie here, as 16 is lesser than my target. The all elements lesser than 16 would be also lesser than my target. So we can eliminate this half. We can eliminate this half entirely. Now, the what does elimination of half mean? Are we going to delete elements from our array? No. What we will do is instead bring our search space closer. Will change our compress our search space so that we will be able to find target more easily. So what I'll do is I'm eliminating the half which I mentioned. We have to eliminate this. We know for sure that 23 does not lie in this half. So what I'll do is just make my low pointer to be mid plus 1. So low would be this. I'll update my low pointer equal to mid plus 1 updation. This is my updation if required. So, and now I know my answer does not lie here. So I'll draw a line here. Now this is my new search space. Now I have to search the element in this new search space, right? So again we will do the same thing. Now calculating mid. So I'll calculate mid, which is just 5 low plus high by 2. My low is 5, my high is 9 by 2. So this would be equal to which is what, 14 by 2, which is 7, right? Yeah, so I'll just erase this. So we have our mid as 7 here, right? Now we will do again the same thing of elimination. So I have the 56 as mid. So I'll check is my I'll just erase this for now. We have our ARR of mid, which is in this case 16. In this case 56. Now it is 56, and our target is 23. So as we can see, as we know, 56 is greater than 23. So my array of mid is greater than 23. I know for sure now this is greater than 23, right? So all the elements which are greater than 56 would be also greater than my target, right? So I can eliminate this half now. I'll check is my mid equal to target. I can clearly see that my mid array of mid is not equal to target. Then I have to eliminate one search space, and it is not, and all the elements which are greater than 56 also would be greater than target. So I don't have to search here. I will eliminate this search space. Now again reducing the search space. How would you eliminate this time? You have to eliminate the right half, right? So this is your mid, this is your high, this is your low, right? If you have to eliminate this half, you'll just move your high pointer here, and this is your new search space. This is low, this is high, right? So what you'll do is just put high equals to mid minus 1. Now you'll do is high equal to mid minus 1 to eliminate the right half of our search space. So this is mid, and now this becomes high equal to mid minus 1. And yeah, let's continue with our example. Now this is also eliminated. Which half is eliminated? Let's denote our eliminated half by red color. Yeah, now this is my search space. This is also eliminated, and this is also eliminated, right? We have eliminated this. Okay, now this is my search space. Again I'll do the same thing. Mid equals to low plus high by 2, which is 5 plus 6 by 2. What is this? 5 plus 6 is 11. 11 by 2 is just integer division is 5. So my mid now becomes 5, which is here. So now I'll check is my mid, array of mid is equal to target or not. My array of mid is 23 and my target is 23. I have found my target. I'll just return. Now as I have found my array of mid to be equal to target, then I'll just return answer as my index 5. Got it? So what are we doing is just eliminating search space, by checking the condition on array of mid and target. How are they is it lesser than target, is it equal to target, or is it greater than target? So yeah, that is how we implement binary search. And like let's discuss, you understood like why are we eliminating the search space, right? This condition, you have multiple conditions, so like let's write down the conditions what we did in this, right? So let's, or we can write it down when we discuss pseudocode of it. So you get the basic idea in intuition. When we write pseudocode, things would be more clear. Now what I need to discuss is like how we eliminate the search space. That's clear, right? The array was of size 10. So initially my search space size, let's call it search space size equal to 10, right? And we eliminated how many elements here? Like in my first iteration of the binary search, I have eliminated these elements. So search space reduces down to 5, right? Let's write it like this. Now search space size is become, has, we have eliminated 5 elements from here. We have eliminated these elements first, right, in first iteration. So now I have to only search in remaining 5 elements, and then after, in my second iteration, I have eliminated these 3 elements. So 5 minus 3 is just 2. Now I have to search in my search space of 2, right? In search space of 2, fortunately I got the element, so we don't have to search any further. So we got the element, right? So what are we doing is like dividing our search space by 2 each time. Let's say like we had a search space size of 64. If we eliminate one half of the array, then we have then search space of size 32. Then we again, if we didn't find the element and we eliminate one half of the search space again, then it becomes 16, and similarly it goes to 8, 4, 2 and 1, right? So what's happening, instead of traversing all 64 elements of the array, now I can just do these many iterations instead of like 64 iterations to like get to my target element. Like 64 represents what power of 2? How many times do I need to divide it by half and half? So this would be just log of 64, right? There's many iterations I need to do, ceil of log of 64. So this just gives me complexity of O of like O of log n, right? This is intuition behind it. So the secondly, like you get the idea of like how do we update pointers, and we'll discuss it. But let's take another example, one more example in our same array but different search space, right? So let me erase this, actually this is not needed. Yep. Now we will do same. We'll initialize our search space like low equal to 0 initially, beginning of the array, and our high equals to end of the array, right? This is 9. So our mid would be equal to what? This would be our mid, low plus high by 2, 0 plus 9 by 2, which is 4. And now is my mid equals to target? No. And I can see that my array of mid is like smaller than target. So if it's smaller than target, all the elements which are smaller than array of mid or also won't be all be small, will be also smaller than target as well. So I know for sure these elements won't satisfy. So I'll update my pointers like this. Let me undo. Yeah, these elements won't satisfy the condition. So my search space reduces down. I'll update my low as mid plus 1. Now my search space reduces down to this itself, right? So again we will do we'll find mid, 5 plus 9 by 2, which is 14 by 2, 7. So this would be my mid. Again I'll check, is my array of mid equal to target? No, it is not equal to 56, is not equal to 30, right? This is 56, this is 30, it is not equal to 30. And my middle element, array of mid, is greater than target. Like 56 is greater than 30, right? So I know for sure that every element greater than 56, which is 72 and 91 here, would be also greater than my target as well. So I'll eliminate my search space again by eliminating the right half. Now I'll just make my high to be equal to mid minus 1, which is 7 minus 1, which is 6, right? So my high would be here. Now my search space has reduced to these elements. We'll do the same again. We'll do low plus high by 2, which is 5 plus 6 by 2, which is 5, integer division. And this is my mid now. Is my mid equals to target? Array of mid equal to target? No. 23 is not equal to target, and my array of mid array of mid is like smaller than target. So every element lesser than 23 would not set would be lesser than target itself. So I can eliminate this search space. So I can eliminate my left half now. I'll move my mid pointer to I'll move my low pointer to be greater than mid. So I'm eliminating this low half. So I'll make my low here and we can search in this right search space. So now my low would be equal to, this was my mid, right? So my low would be mid plus 1 now. So this is my low now and this is my high. Now high and low overlap. So now mid would be 6 plus 6 by low plus high by 2, which is 6 plus 6 by 2, which would be 6 itself. So this is low, high and mid itself, like it would point to 6 itself. So now I will check, is my mid equal to target? Is 38 equal to target? No. So and 38 is greater than target, right? So if 38 is greater than target, 38 is greater than target, so I can eliminate the right half. So I can eliminate the right half of it. So I know for sure that my answer does not lie in right half. So my high becomes mid minus 1. And now you can see if high becomes, this was mid and this was high itself. So now high becomes mid minus 1. This is our high. So let me just erase unnecessary stuff. Yeah, this is my low, this is my high. As we knew, like 30 does not exist in array, and now my low pointer, my low is here, my high is here, my low is now greater than high, my low is greater than high, which means target does not exist. If I didn't find the target till now, we have exhausted our search space. This was my search space. Now this is my low, this is my high, and now this is like this. This is low, this is high. This doesn't make sense, right? So we have already exhausted our search space and we still didn't find the answer. That means target does not exist, right? So if we have this, like after doing proper binary search, applying conditions, and still we didn't find we exhausted our search space by seeing like low is greater than high, then we can clearly say that the target does not exist in array, right? So let's talk about the pseudocode. Like let's have a function, let's call it binary search. On we have an array, right? So I can initialize two variables. Let's call it low, which would denote the start of the array, which is 0, and we can have our second variable int high equals to end of array, which is, let's say array is of size n. So let array is of size n, so high would be just n minus 1, right? So now to iterate binary search, we will use a while loop. Let's we'll discuss what would be inside while loop later, what should be the condition. Now what we do in binary search, we have this search space of low to high, right? This is my search space. I would find middle pointer in the search space. So my mid equals to low plus high by 2, right? This would be my middle, right? And now I'll see if my array of mid is, if it's equal to my target. If it's equal to my target, then I can just return mid. I have found the answer. Like this, if this holds, this means that like my array of mid is equal to target, we have found the answer, just return the mid index, right? Now there can be two cases. Else if my array of mid is greater than target, either it would be less than target or it would be greater than target. So let's if it's less than target, let's write it like this. If it's less than target, now I know that my target lies in right half, so I'll just update my pointer to be low equal to mid plus 1. I'm eliminating my left half by updating my low pointer. And else, this case basically says that if array of mid is basically greater than target, I know that now my array of mid is greater than, if target lies here, let's say this is my target and this is my array of mid, so it's greater than target, I need to eliminate the right search space, so I need to search in my left search space. To eliminate right search space, I'll just update my high pointer to be equal to mid minus 1. Just take a pen and paper, try to implement the same example as I've given using this pseudocode. You'll get complete clarity of this approach. So this is how you update pointers, this is how you write the pseudocode of it. And for condition, for while condition should be a valid search space, right? We have a valid search space if and only if we have our low pointer is less than equal to high pointer. If this holds, this is a valid search space, right? If I can explain it right here itself. So this is my low and this is my high and this is my search space, but this is a valid search space. And if this is my low, this is low and this is high as well, this is also valid search space where low is equal to high. You have one element to search for and the mid would be obviously equal to this element itself, so this is also valid search space. But what if now we have something like this is high and this is low. Now this is not a valid search space, like high should be always greater than or equal to low, so this is not a valid search space now. So this is not a valid search space, so we'll all break out of our while loop and we don't have an answer if we didn't find answer yet, right? And if we didn't find the answer, we can just return -1, like just denote this, just denote answer not found. Right, so this is the pseudocode of it. And next we need to discuss, we discussed example, we discussed pseudocode, we will do actual code as well, and how to prevent overflow and time complexity. We have discussed time complexity of binary search. As we eliminate our search space by 2 each time, this just means that we eliminate each search space by half, right? So we keep dividing our array size by 2 each time. Then how many times do I need to divide this by 2? And every time in each iteration I'll eliminate the search space. So every time I divide the search space by 2, which means how many times can I divide my array of size n by 2? Log n times. So yeah, my time complexity would be O of log n. And my space complexity, as we see in our pseudocode, we are just using constant space. We are using like 1, 2 and 3 variables here, 3 extra variables. So we are using constant space, so we have constant space here, right? So let's write the code and then we will like discuss this about the last thing about what overflow case later. So let's write the code. This is the same problem, given an array of integer nums which is sorted in ascending order. As I said, our array should be sorted. If array is sorted and we have any like sorted in decreasing or decreasing or increasing order, then we can use binary search. And okay, so array is sorted, array nums is sorted, and we have an integer target. We have to write a function target in nums such that if target exists, then we have to return its index, and this assumes 0-based index, I guess. Yeah, otherwise return -1. So we'll just write the algorithm like we have discussed. What we have to do is just initialize 2 pointers, low is equal to 0 and high equals to n-1, where n is size of our array. So like let's write n equals to size of our array, which is size of nums, right? This is like how we initialize our search space. Now while my low is equal to is less than equal to high, then we have a valid search space as we discussed. I can write my mid equal to low, I have to use brackets, low plus high by 2. Now if my nums of mid is equal to target, then I have found my answer. I'll just return mid, assuming this is 0-based indexing. Else if my nums of mid is like lesser than target, if it's lesser than target, I'll eliminate the left half, and search in right half. To search in right half, I'll move my low pointer to mid plus 1. Now this is also done. I'll move my low to here. So low just becomes mid plus 1. And else if I have to eliminate the right search space, if my basically this is nums of mid greater than target, if it's greater than target, I know now my nums of mid is here, my target is like here, then I have to eliminate the right search space like this one. So I'll just move my high to be mid minus 1. So as we discussed in pseudocode, this would be equal to high equal to mid minus 1, right? And if we find the answer, whenever we find the answer, we'll just return mid here. And if we do not find the answer and we like exhaust our search space, the high is now greater than low, then I can just return minus 1. We have exhausted our search space and we did not find the answer. Let's try to submit it. This should run fine. This is accepted and submit. This is submitted as well. Yeah, this got accepted. But as we see, our constraint like num's length is 10 to power 4. Okay, but what if now let's talk about the overflow case. Let's just to our iPad again. So talking about the overflow case, what if as we are using integers here, right? So if my low, let's say equal to int max, and my high also becomes in some case int max, so when I calculate the mid, it would be low plus high by 2, right? This is low plus high by 2, right? So it would become 2 int max, and mid all is also an integer, right? So it would become 2 int max by 2, and this would overflow as like if we calculate 2 into int max and try to store it in int variable, this would overflow and this would give you wrong answers. So like how to fix it? To fix it, the simple approach is like we can instead of assigning, I know that my mid always lies between low and high, right? But to avoid the overflow, we can just make our low and high to be long so that this does not overflow. Or we can do this to like 1 ll into low, 1 ll into high, right? We can convert this whole calculation into long so that it doesn't overflow, or also like make our mid long just to be safe, right? We can do this. Or more elegant way to do this is like we know basically mid equals to low plus high by 2, right? What I can do is, let's say I add a low and I subtract a low. It is the same thing. This would be low plus, now I'll just take the LCM and just cross multiply. So low plus high minus 2 low by 2, and this would just give me low plus high minus low by 2, right? So this is my new mid. Simple maths, simple manipulation of numbers. Now how is it different from our this one, the simple low plus high one, right? We have made a mess here, so I'll just clean it up. So how is it different from my mid equals to low plus high by 2? So I can just say that in this case low plus high ka sum would exceed int max and this would cause problems. But in this case my low is lesser than or equal to int max, that's fine, and my high minus low, this difference would be also less than int max, right? So this sum, this difference actually is lesser than int max, and this is also like at max int max. So this I know and know that mid is like in the search space, like in the range, so this won't overflow now, right? So by making the simple change, now we have prevented the overflow, like we have prevented the overflow, and that's how we do it. We'll do it in code as well. So just one change here to prevent overflow. In interviews, this is very useful. You can just explain this to interviewer as well. He will be very happy. You can just do mid equals to low plus high minus low by 2, and this should also work fine. Let's run it, submit it as well. So yeah, that's it. And I guess that's it. We have wrapped up our discussion on binary search. This is a simple problem. We will discuss more problems in our further videos. So yeah, I think everything is clear now. We have discussed how to prevent overflow as well, time and space complexity as well. So yeah, thank you. Bye bye.